Yes, so in this paper, they construct some attacks that basically allow them to extract the information of actual individuals that were used to train the language model GPT-2. And these attacks are very simple. They consist of like carefully specified queries into the model. So for example, they entered East Stroudsburg, Stroudsburg, and some other words, and they got the language model, the chat bot, to spit back some text that it memorized, which contained the contact information of a real person, Peter W, in the data set. So clearly this is not a desirable situation, and we really need some additional safeguards when we're training these models to prevent, catastrophic privacy breaches. To that end, we'll consider differential privacy, which is the gold standard of rigorous data privacy notions. To define DP, consider a dataset X with ended individuals and an adjacent dataset X prime that differs just in the data of one person, say the nth person. Then if an algorithm is M is going to be DP, then when we use it on X and we get some outputs, say training some neural network, and then we use it on X prime and get some other neural network, then these outputs should be similar. A bit more precisely, algorithm M is said to be epsilon delta differentially private if for all adjacent data sets X and X prime and all measurable subsets S contained in the range of M, we have this inequality in pink holding. So this basically says that no adversary can learn much more about any individual in the data set than they could have learned had that individual never contributed their data in the first place. So basically it restricts us, it means that we can like draw population level inferences based on the output of the model, but we can't really learn micro level information. In particular, this definition precludes the sort of like data extraction attacks that we saw on GPT-2. Memorization of specific information about a person would not be allowed under differential privacy. And the amount of privacy that we get is quantified by the privacy parameters epsilon and delta, with smaller epsilon and smaller delta, providing a greater level of protection. An important fact about differential privacy that we'll need is that if the sensitivity of a query Q is bounded by S, meaning that this symbol here, this tilde, means X is adjacent to X prime. So if we replace one point in X by another point in X prime, then the output of the query should not change too much in L2 norm. It should be bounded by S. And if that's the case, then simply adding carefully calibrated isotropic Gaussian noise to the output of Q provides differential privacy. So we need the noise variance to scale roughly with the sensitivity squared over epsilon squared times the logarithmic function of delta. So you can see that as epsilon and delta gets smaller, we need to add more noise to ensure to provide that greater level of privacy. Okay, any questions on the definition of differential privacy before we move on? Okay, so we're going to consider the problem of differentially private stochastic optimization. So our goal is to find a differentially private approximate solution to this stochastic optimization problem given here. So we want to minimize the expected value of the loss function, where the expectation is taken with respect to some unknown distribution D. So that you can think of this as minimizing the test error or the population loss. So here little f is a loss function, which for most of the talk we'll assume f is convex. It's defined on a convex compact parameter domain in Rd, W, and then x here is a data universe. It can be any set. And the distribution D here is unknown, and that's what makes this problem challenging. We're only given access to n IAD samples from the distribution, but we don't exactly know the function that we're trying to minimize, so we need to estimate it. And because we don't have exact access to capital F, we can't necessarily hope, even non-privately, we can't hope to make to find the exact minimizer of F. So we'll measure the performance of an algorithm A by its excess risk, which is defined like so. And here the expectation is taken both over the random draw of X and possibly over the randomness of A if A is a randomized algorithm. Clear so far? So a bit of background on differentially private stochastic optimization. In the case where the loss function is uniformly Lipschitz, meaning that this red inequality is satisfied, so we have the stochastic gradients of the loss function are uniformly bounded by some parameter, uniformly over not only all parameters W, but also over all data points in our universe. In this case, the excess risk of the optimal DP algorithms is understood. And Basili et al. In 2019 provided tight upper and lower bounds on the excess risk that look like this. So here the
question.
Yes.
What's the norm here?
L2 norm throughout. Yeah. Good question. So here, this is the optimal excess risk of differential private algorithms for solving stochastic optimization with uniformly Lipschitz laws. And you can see, first of all, the first term, 1 over square root of n, is roughly the non-private rate. And the second term here can be seen as the cost of privacy. So you can see it increases with the dimension of the problem, the number of model parameters, and also increases as we shrink epsilon and delta, which is intuitive. And importantly for us, it also increases with LF. So if LF is very large, potentially we get vacuous excess risk. In practice, LF can be huge due to outliers. As an example, consider linear regression.
Sorry, just another question about this basic result, like the for epsilon differentially private without delta, what we get, just on
good question. So if you want the stronger notion of pure differential privacy, meaning delta equals 0, then instead of a square root of d in the numerator, we get a d in the numerator.
I see. And always it's kind of the second term is kind of almost always there, but this one dominates as soon as delta is bigger than something, or how does it work?
Yeah, exactly. So this is the bound, and yeah, so you can see that, for example, if epsilon is like 1 and d is 1, say a very low dimensional problem, then in that case you basically get privacy for free because the dominant term is the non-private 1 over square root of n term, right?
Mm-hmm.
On the other hand, if it's a high dimensional problem, and even if epsilon is 1, but say d is n squared, then all of a sudden the cost of privacy is huge, and you basically get like get a trivial bound.
Yeah,
that makes sense. So yeah, you can get privacy for free, meaning privacy for free. When I say that, I mean that the non-private term is the dominant term. So basically there's effectively no cost of privacy except for some constant factors. And that happens whenever this term is smaller than this term. And so that happens whenever like either epsilon is very large or d is very small.
see, and just to understand, maybe it's out of the scope of the talk, or we can discuss offline, but just a looming question is, if the loss is not Lipschitz, it's like squared loss, right?
That's basically that's what we're answering.
Okay, I see. Because the thing is that if it's a squared loss, well, first of all, I mean, it means that, squared loss, of course, is not Lipschitz, right? On the other hand, to me, it seems that it might be in a way not the right loss, because if you want to make things private, you would make, instead of square, you would make cuber, because privacy is somehow related to robustness. And you don't want to get this kind of huge tails of the loss that go like, maybe, I don't know.
That's a good point. Yeah, but you also want to be able to do like basic things like linear regression privately without.
Now, maybe inside is what you're doing in a way, but like, I don't know.
Yeah, no, that's a good point. But yeah, so yeah, exactly as Dimitri said, this Lipschitz parameter might be infinite, or even if it's not infinite, it's huge. So in the case of linear regression with square loss, if we just have one outlier sample with very large norms, say 10 to the 6th, and even if our parameter domain is compact, say a unit ball, then we end up with LF being 10 to the 12th. So then we get some excess risk bound, which is like, scaling with 10 to the 12th. And this is enormous, and it's very likely that the trivial algorithm that just randomly outputs any point in our constraint set does better than that, because that would give you like excess risk scaling with like 1, basically, with the Lipschitz parameter, like population loss, which is much, much smaller. So that's one example. If you went with unconstrained, if you went with linear regression with the data universe being all of our D, then in that case, linear regression would have an infinite. LF would be infinity, so you would get completely vacuous excess risk. And this is just one example, but there's many situations in practice. You can calculate this worst case Lipschitz parameter on data sets, real data sets, like even for neural networks on MNIST or something, to calculate it empirically and see that it's very, very large. And so these excess risk bounds that the previous works proved can become vacuous in that case. And even when they're not vacuous, they can be very pessimistic. So the goal of this talk is, the first question is, can we relax this uniform Lipschitz assumption to allow for more optimistic excess risk bounds? In other words, can we get excess risk bounds that scale with something else besides this uniform Lipschitz constant, worst case Lipschitz constant? To that end, we'll consider stochastic gradient distributions with bounded kth order moment for some k greater than or equal to 2. So we consider distributions of loss functions satisfying this inequality in green. You see what we've done essentially is replace the supremum over all x with an expectation over all x. So instead of the worst case Lipschitz parameter, we're considering some sort of average Lipschitz parameter. And so clearly RK is always less than LF, but this inequality is often very loose. Returning to the linear regression example, if we assume now that the data distribution on X is a one-dimensional truncated normal, then with unit variance, then we can see these moment bounds are all reasonably small. R2 is less than 5, R8 is less than 14. You can keep going. R100 still isn't that big, but LF is enormous. The worst case Lipschitz parameter is much, much bigger. So
even with supremum inside of the expectation?
Yes, even as it's defined here, yeah. So that's a good point though. So if we switch expectation and supremum, then this parameter becomes the new parameter. If we define it with expectation and supremum switched, is going to be something smaller. And we actually give tight upper and lower bounds under that assumption as well.
What is the factor roughly? Like let's say if everything is normal as it can be.
What's the difference between the one with the supremum?
Yeah.
I don't know if I actually looked at like examples of that. They're actually very similar in, if the data is bounded, they're like exactly the same. Because like the lower bound basically, what?
Yeah, if the data is on the ball, you're saying it's the same. Right?
They're the same, at least, maybe not always, but at least in the distribution that I constructed to prove the lower bound. So I ended up proving the same lower bound under both assumptions, no matter what order the expectation and supremum are in, you get the same lower bound and the excess risk essentially. And then upper bound, we end up showing this, so we can show an upper bound with the expectation and supremum switched, as long as the distribution is sub-exponential. I think but we should be able to get rid of that assumption with like a better analysis maybe. Any other questions? Okay, so the key question that we want to address in this talk is, given some parameter RK, some moment bound RK, privacy parameters epsilon delta, access to NIAD samples from some unknown distribution, and D model parameters, what is the minimum achievable excess risk that any differentially private algorithm can attain? And our contributions are as follows. So first we characterize the optimal excess risk of differentially private stochastic optimization under the bounded kth moment condition for both convex and strongly convex loss functions. We show that the excess risk in this case depends on the moment bound rather than the worst case Lipschitz parameter, which allows for significantly faster rates in the presence of outliers or heavy-tailed distributions. Along the way, we developed some new techniques. We come up with a novel algorithm for proving our excess risk upper bound, and we also come up with some results that might be of independent interest that involve, for example, bounding the stability and generalization error of learning algorithms for non-smooth, non-uniformly Lipschitz loss functions. Second, we devise some linear time algorithms for smooth convex losses. So if we have smoothness, we can actually use acceleration to get some algorithms that run in linear time. And these algorithms have nearly optimal excess risk. So in certain practical parameter regimes, they're essentially optimal, but not in every regime. Yes.
Well, we can discuss offline, but I think there's still like if you compute squared loss, right? So if you say XTW, like forgive me if I make any numerical error, but it seems to be a very basic example. So your loss is XTW minus something, minus unknown thing, all of this squared. So this XTW minus A squared, where A is something unknown.
Yeah.
Right. Then when I take the gradient, so this is f of XW. Take the gradient and W of this thing becomes X times X transpose W minus A, right? Now, when I take supremum first in W, let's say over the unit ball, right? It can be at large. The norm of this thing, squared norm, is the squared norm of X. If X is standard normal, scales is D.
Right.
dimension.
Yeah.
So I took first supremum, then expectation.
Supremum, then expectation.
But if I do first take expectation in X and then supremum, right?
Yeah.
Don't I get this Z? Don't I get it? Don't I get something like something else?
So you're
Because
gonna
what
W
happens is
uniform.
XTW goes like I first take expectation, right?
Right.
So it's like let's say W is so it's invariant problem, so I can just without loss of generality now it becomes like without super W is E1, right? So I have X times X1. And so I have chi-squares, so x1 squared plus a bunch of uncorrelated guys.
Yeah.
When I take their expectation, it's just only this guy remains, and it's 1.
Okay, so I'm not claiming that they're always equal. That's probably correct. I'm not claiming that switching the supremum and expectation has no effect. I'm just saying it has no effect on the optimal minimax optimal access.
No, I understand what happens. That is you know like you still replace maximization over all x's
Right.
with like some averaging over x's. As a result, you have distribution of x with unbounded support.
Yeah.
You get something was infinite, and now of course it's finite. I'm just still saying that you're losing the dimension there. So it's probably there is a way to accelerate it if there are no, like in your setup, if there are no matching lower bounds that match up to dimension as well.
Yeah. Yeah. So in our case, it turns out like in our appendix we have matching upper and lower bounds for under the switching.
So just still, it's like it,
But yeah.
might be like in a way, as Israeli people say sometimes, maybe like it's time to break the lower bounds. So like assume something.
So assume something different.
Yeah,
that's
because
a good point.
it's like super of the expectation would be, and might be a deeper thing too. But anyway, not a deeper, but also a deep by itself to look there. Anyway,
That's a good
so-
point. Yeah. Okay. And so this is our second contribution is linear time algorithms. And then third, we're going to turn to non-convex loss functions, which satisfy the so-called PL inequality. And in that case, we give algorithms with near optimal excess risk, and they also run in linear time. So start by talking about the excess risk of convex differentially private stochastic optimization with bounded Kth moment. So in this case, we have the following theorem. If f is a convex loss function, and the parameter domain W is convex and compact with diameter bounded by D, and we have this bounded Kth moment condition satisfied, actually bounded to Kth moment, then there's an efficient epsilon delta DP algorithm with excess risk given like so. So the first term here is truly the non-private rate, RD over square root of n. This one, before I kind of lied because it's silly, the first term is LFD over square root of n, which is not actually the non-private rate. Here we actually have the non-private rate. It's got the right scaling with R instead of LF. And then the second term is the price of privacy. So we can see that because the bounds scale with R instead of LF, we get faster rates in the presence of outliers. Also note that as K goes to infinity, the second term recovers the, as K goes to infinity, our bound recovers the uniformly Lipschitz bound of Basili et al., which makes sense because if we have infinitely many moments, that's the same as saying that your loss function is uniformly Lipschitz. And in general, as K gets bigger and you have more moments bounded, then your excess risk gets smaller, which makes sense. The function is becoming nicer. On the other hand, as K gets bigger, this RK parameter might also get bigger. So it's kind of a balance. You know, if you let K go to infinity, for example, then R infinity is LF, the worst case Lipschitz parameter, which could be enormous as we saw in these examples. So in that case, you probably might get worse excess risk in practice. Yeah.
So obviously, I mean, by using R2K or LF, the theoretical result will be very different. But in terms of algorithm, is it actually the same or?
No, we'll see. It's a very different algorithm. Yeah. And so we also show lower bounds that are almost tight. So optimal up to a logarithmic factor and the dependence on R2K instead of RK. So we're not the first to consider this problem. There were some prior works, a pair of ICML papers by Wang et al. 2020 and Kamath et al. 2022, considered essentially the same problem, but gave suboptimal excess risk. These works also required uniform smoothness of the loss function in the W variable. So they require the loss function to be differentiable and to to have Lipschitz continuous gradient with Lipschitz parameter of the gradient being uniformly bounded by beta f. And this is actually a restrictive assumption setting because that actually implies uniform Lipschitz continuity for LF being less than beta f times d. So those works basically assumed that that the gradient is Lipschitz continuous uniformly over all x.
Operational loss.
That's what these works assumed, and they also specifically assumed that beta f was like less than 10 or something like that. And then this actually implies that the loss function is uniform for Lipschitz with LF less than or equal to beta f times d. So this is very restrictive. Now all of a sudden you're assuming you're losing the whole essence of the problem. The motivation for the problem is LF can be huge, 10 to the 12 or infinity. And here these guys have basically said, oh, never mind, we'll just consider where LF is less than 10 times the diameter of the constraint set, which is assumed to be finite. Okay, so basically we make advances over those prior works on two fronts. First of all, we get tight excess risk bounds up to a logarithmic factor, and we do so under more realistic, more relaxed assumptions, getting rid of this smoothness
So
condition.
I just forgot, everything is convex though?
Yeah, well, we'll consider non-convex at the end if we have time.
So this is true for convex case. Otherwise, only if the minimum is inside.
Yeah, so the paper's prior works for convex, yeah. Okay, so before we get into our algorithm, let's warm up by talking about the optimal DP algorithm for the simpler uniform Lipschitz case. In this case, the simple noisy differentially private stochastic gradient descent algorithm is optimal. So how the algorithm works is basically this looks very similar to the updates that you would get by doing projected stochastic gradient descent, except that here so you just ran in each iteration, you select a random index IT in index T from your data set, and then you compute the stochastic gradient at that point at the previous iterate WT. And then you update your parameter by taking a step of projected SGD, but here we're adding Gaussian noise. So this is privacy noise that's calibrated to ensure epsilon delta differential privacy. And in fact, it's not hard to show that this algorithm is differentially private if the variance of this privacy noise is calibrated roughly like this. So it should scale with the worst case Lipschitz parameter over epsilon squared. And that's because, as we saw basically by the first slide, if the sensitivity of this stochastic gradient update is bounded by 2 times LF, which holds basically the triangle inequality, then this is sufficient to ensure differential privacy. And the excess risk proof of this earlier work basically goes in 2 steps. First, they bound the empirical risk, which is fairly trivial actually, because it basically follows from like existing results on convergence of SGD. It's just that the variance of their stochastic gradient oracle is now larger because you're adding Gaussian noise to it. And then the second step is to bound the generalization error. And they do that by using a uniform stability argument. So uniform stability refers to basically how much the loss function changes when as a function of A of X, when you replace a data set X by an adjacent data set X prime. And it's known that if an algorithm has uniform stability bounded by alpha, meaning this quantity in turquoise is less than or equal to alpha, then its generalization error is also less than or equal to alpha. So if you have an empirical risk bound and you have a uniform stability bound, then you put them together and you get how well your bound does on unseen test data, how well your algorithm does on unseen test data. And
so the first line actually, so sigma square is really large, so it's a very large.
yeah,
noise.
So yes, exactly, very large noise. I am kind of hiding some of the details here. It turns out that you can use like what's called privacy amplification by subsampling to get like an n squared term here. So it becomes much smaller, but this is, I just wanted to highlight the important parts of the noise for where our noise is going to differ from theirs. But yes, it's very large because it scales with LF at least, even if there's the n squared. Yeah. And so, yeah, exactly. This is the problem, is that the LF can be huge, and that means we have to add huge privacy noise. And it also means that the stability bound that these guys got, which also scales with LF, is huge, and that leads to huge excess risk. So can we modify this algorithm to get optimal rates for bounded RK case? In particular, we want to get rid of the dependence on LF. Okay, so one first idea is the following simple modification. Instead of doing DPSGD, we're going to do clipped DPSGD. So we're going to clip the gradients to control the sensitivity and allow us to reduce the amount of privacy noise that we add. And when I say clip, I mean basically instead of using the stochastic gradient here, we're going to use a scaled down version. We're going to truncate the stochastic gradient. So if it's got norm bigger than C, then we're going to rescale it to put it back in the ball of radius C. And by doing this, this allows us to reduce the amount of noise that we add. Because now instead of the sensitivity of our updates being 2 times LF, the sensitivity is now 2C. And this means that we can replace LF by C in our privacy noise expression. So in particular, if C is much smaller than LF, then we're adding much less privacy noise. But this was essentially the simple modification that was considered in these earlier works, but these earlier works did not get optimal excess risk using this algorithm. And an important reason why is because, first of all, clipping introduces bias into the estimator, right? The estimator is no longer, the stochastic estimator of the gradient is no longer unbiased because we're clipping, potentially, for example, if the clip threshold goes to 0, then we're just sending all the stochastic gradients to 0 and not using any of the information, and it's going to be a completely biased estimator. And also clipping hurts the stability of DPSGD. So these earlier works, instead of basically they couldn't bound the stability of this algorithm. So instead of doing that, they resorted to what did they do? So one of them did a 1-pass algorithm, which just wasn't able to get enough, the optimization error small enough. And then the other used some other technique for bounding the generalization error, which resulted in like a suboptimal dependence on the dimension. Yeah.
Since we're discussing this, there are recent works like 2-3 years ago, starting from actually Uditsky, and then there was a follow-up by Drusviatsky and Davis, where basically if you do stochastic approximation, robust stochastic approximation with Lipschitz laws without any privacy but robustness, so you want to have only weak bounds on moments, finite moments without heavy tails, then you can get like a robust result, heavy tailed result. And there they also do clipping. Clipping is the main tool, and they do bias variance trade-off. And it turns out that with the clipping, the rates are optimal. Like essentially with the right regime of clipping, choosing the threshold and doing the right analysis, somehow magically it turns out that you don't lose anything.
Yeah.
After some logs.
That's
so just like one thing you're
interesting. Yeah.
It might be very much related to what you're talking about.
Yeah, definitely. Yeah, I mean, so and the bounds that they got weren't completely terrible, especially in the strongly convex case. I think it was like only suboptimal in terms of the dependence on the kappa. Of course, they needed smoothness.
Mm-hmm.
But yeah, so we're going to do something a little more sophisticated, but we're going to use this as a building block, this clipped.
But just you mentioned the results I mentioned, all of them are optimal.
Optimal.
Yeah.
I think, yeah, that's interesting. I'll have to look at that. Yeah, I guess without privacy, it might be possible. So can we devise, like, of course, this algorithm is very hard to bound the stability because of the bias introduced by clipping. So our approach is going to be to try to devise a stable algorithm in order to get optimal excess risk. To that end, we're going to consider regularized empirical risk minimization. So here, this is the problem of minimizing an empirical loss where you add an L2 regularizer to it. So here, lambda is some positive number that we can choose freely, and W0 is just any fixed point in our constraint set. And so consider the following algorithm 1. We're going to solve this regularized empirical risk minimization problem using a noisy differentially private stochastic gradient descent with selective clipping. So when I say selective clipping, I mean we do the following. So we're going to clip, notice that the gradient of this regularized empirical loss is like this. Gradient of FWX plus lambda over 2 W minus W0 squared. This is just equal to the gradient of F plus lambda times W minus W0. So a naive approach would be to just clip this entire quantity, but we're going to do something more careful than that. We're just going to clip the first term, the gradient of the loss function f, but we're going to leave the second term untouched. And the reason we do that is because the second term doesn't depend on the data. It doesn't depend on x, it only depends on w. So we don't need to clip it for privacy reasons, right? The whole point of clipping was to reduce the sensitivity of our updates and reduce our privacy noise. But in this case, the second term doesn't contribute to sensitivity because it doesn't depend on the data. So if we tried to clip that whole thing, that would cause our bias to explode. So by doing this selective clipping, we're able to reduce bias significantly, and this reduction in bias comes at no cost to the variance of our estimator. And we show the following proposition.
Quick question.
Yes.
What's sigma nu?
Sigma nu. Yeah, so it's going to be some noise, some new noise that's calibrated roughly to like the clip threshold over epsilon squared. It's going to be similar to our old noise, but except that now we have to consider the sensitivity. I guess actually it's going to be exactly the same as sigma squared clip on the previous, like c squared over epsilon squared times log 1 over delta. Yeah, because for the reason being that this term doesn't affect anything. It doesn't contribute to the sensitivity. So yeah, sigma squared nu is actually gonna look like sigma squared clip that we had here. Okay, so we show the following proposition that regularized ERM is on average model stable. Here I'm not even, this proposition has nothing to do with privacy, nothing to do with noisy DPSGD. It's just saying the process of finding the minimizer of the regularized empirical loss is a stable algorithm, meaning it generalizes well. And this might sound like, oh, this clearly has to be some classical result. And indeed it is if you assume that the loss function is uniformly Lipschitz or smooth, but in fact, we have to prove basically a new result, a new basic result in statistical learning theory by proving this result for non-uniformly Lipschitz loss. Like specifically, we extend a result of like Shalov-Schwartz from 2009 to the case where without uniform Lipschitz, we show that basically uniform Lipschitz isn't necessary. You can replace it with this weaker moment-bound condition and get the same result. And here, when I say on average model stable, this is a weaker notion of stability than uniform stability, which is necessary in our case because we're working on our weaker assumptions. So instead of requiring the bound to hold uniformly over all data points X, and instead of being concerned with how much the loss function changes, here we're only concerned with the output of the algorithm A. So we require that A on average, when we take expectation over A and expectation over a certain coupling of adjacent data sets, then this distance can't be too big. And it turns out that this weaker notion of stability is also sufficient for generalization. So it was known previously that uniform stability implies generalization, but here we show that on average model stability is also sufficient for generalization. And again, this is a result that was known from a 2020 paper in the case where the loss function is uniformly Lipschitz and smooth, but here we show that neither of those conditions is necessary.
Just understand generalization in average, right? So in terms of expectation of the population risk of your estimate minus optimal population.
Yeah, exactly.
It's been, as far as I understand, it's been a long-standing problem to do high probability, like in probability versions of stability of this reduction.
Yes, that's much harder.
It's been like solved maybe a couple of years ago, like a year ago, something like that.
Yes, I think there is a paper by Feldman and Von Drack.
This kind of stuff.
Yeah, so I don't think I think probably using their techniques, we could get this same sort of result for high probability, but we'll just focus on expectation for simplicity here. And then the third proposition is that algorithm 1 finds an approximate ERM. So these first two propositions, very general, learning theoretic, and hopefully of independent interest for anybody who's working on learning theory or that type of thing. But the third one, it relates specifically to this differentially private algorithm. And that basically is just sort of showing that, SGD, if you consider SGD with biased and noisy stochastic gradient updates, then you can bound the error of the algorithm in terms of the bias and the variance. And by putting these propositions together in the right way, we can get a proof, we can get an excess risk bound for algorithm 1, an excess population risk bound for algorithm 1. Unfortunately, that excess risk bound is still suboptimal. But this begs the question, can we use algorithm 1 as a building block and derive a truly optimal algorithm from it? To that end, we're going to consider the iterative localization technique of Feldman et al. 2020, and we're going to combine that with algorithm 1 in the right way. Let me walk you through this algorithm. So we start out with some parameter W0 in our constraint set. We initialize anywhere, and star here denotes the optimum that we're trying to find. Okay? We're trying to get close to that optimum while preserving privacy of the data. Okay, so in the first iteration, we so in the first line of the for loop, it's going to run in a logarithmic number of steps, as you can see in line 2, and then we're going to draw a batch of ni samples from X with our replacement. So when I equals 1, we're actually drawing half the data in the first step. And then we're going to form this regularized empirical loss here. And then we're going to use algorithm 1, which was the noisy SGD algorithm with selective clipping, initialized at W0 with this privacy noise and a certain careful choice of step size to minimize this regularized empirical loss over the constraint set. So when I equals 1, Wi is just equal to our full constraint set, W. And that's going to result in this, this parameter W1 that we get here. Then after this, we're going to shrink the diameter of our constraint set and form some new smaller constraint set that's centered around W1. We're going to do this shrinking carefully with, sort of geometrically decreasing diameter. And we're also going to shrink the step size and the clip threshold.
Sorry, I really don't understand. Why don't we do both? Why we have to do both lambda and the DI? Because DI seems to be controlling. Do I understand correctly that DI is the constraint? So you have penalty and the constraint.
It turns out you kind of have to do it all, and you have to tune all these, use all these degrees of freedoms in the right way to get the optimal range.
But you increase the lambda probably twice, decrease the diameter twice, or no?
Something like that. Yeah, it's like it's like one goes up from like one scales with like 4 to the I, and the other decreases with like 2 to the I, something like that. Yeah.
So one more question. How did you choose the diameter of the new ball here?
Yeah, so I didn't specify it here because I wanted to keep it simple on the slide,
Okay.
but it decreases geometrically. So it's something like the previous diameter over 2 to the I. So we'll like basically cut the diameter in half in the first round, and then the next round we cut it by 1/4, and it gets smaller and smaller.
So how about the initial diameter you choose?
The initial diameter is given to us.
Given.
It's so we're given some constraint set, and then we're trying to find the optimum. Right? And so when we shrink the diameter, the point of that is to shrink the optimization error and reduce our search space, right? Because then you can look carefully at the sort of SGD convergence, it scales with the diameter of the constraint set. So if we shrink our diameter, then in the next phase, we're going to be able to get a more accurate solution. The point of shrinking the step size and the clip threshold is that those decrease the effective variance of our privacy noise. Also shrinking this, because remember the privacy noise scales with the clip threshold. It also scales with the step size, the effective variance does. And also the shrinking the step size prevents us from moving too far away from W1 and hence from W star. And then increasing the regularization parameter is going to improve stability and also going to sort of play the similar role of shrinking the step size in preventing us from moving too far away from W1. Yes.
Just sorry. So just probably you actually thought about yourself when you were doing that. Just like in case if unnoticed, I would just suggest thinking about all the things that scale together so that their product, like if the things here scale geometrically up and down, that means that the product, like you can couple them in a way that the product remains the same.
Yeah.
Probably respecting the units of these things would suggest you what's going on in a way, in a more like intuitive terms.
Yeah.
Like if, for example, if every time you increase I, like one quantity scales like 4 times and another one scales down like 2 times, that means that the first quantity times the square of the other is an invariant. And like looking at this invariance might suggest you what's going on, because you might in fact potentially, I don't know, but potentially it might be, there might be a simpler procedure it kind of gets the same effect. Even in the initial paper. I mean,
Yeah, in the Feldman. Yeah, potentially. I think you kind of need all these degrees of freedoms to get the optimal rate because they don't scale exactly. I mean, yeah, I think you kind of need them all. It is my
just
I haven't tried like put a lot of effort into trying to
I
reduce it,
understand. It's just
but yeah,
basically like
it's a very good point to think about. Yeah. Okay, so then like we remember we shrink the diameter, shrink the step size, shrink the clip threshold, all to decrease privacy noise for the next round, shrink the optimization error, and we increase regularization to improve stability. All right, so now we're going to go back up to the top of the for loop. So now I equals 2. So we're going to draw n over 2 to the negative I, n is equal to n over 4. So we draw fewer samples this time without replacement. We form a new regularized empirical loss using this new batch of samples in line 4. And then again, we run algorithm 1, but now we're initializing algorithm 1 at the point W1. Okay, so we're starting at W1 and we're trying to move closer to W star. All right, so we're using this empirical loss here, using the new batch of samples. We run algorithm 1, noisy clipped SGD with selective clipping and new privacy noise because CI is now smaller. And we're doing the minimization over this ball, this smaller ball, W2. All right, and we do that and we get some new point W2 that's even closer to W star. Okay, and then we go back down, we change parameters again, decreasing DI, step size, clip threshold, increasing lambda. And this process repeats for a logarithmic number of iterations until we've exhausted all n of our samples.
Excuse me, when we construct the W2, do we know the star is inside the W2?
Yeah, very good question. We had to prove that the right choice of new diameter ensures that we still have W star in there. Yeah.
So that's the reason why you take a log, right? It's on either in this side or that side, right? It's like a binary.
Why we take log?
Yeah.
That's log. That's just kind of because. So at the end of the day, we want to use every sample once.
Right.
We don't. If we reuse samples, that makes it much harder to prove like generalization bounds.
Stochastic approximation.
Yeah, exactly.
So in the end, is there a logarithmic overhead because of this procedure, or in the end, it doesn't even have an extra logarithm?
In terms of why do we have a log in our excess risk bound, you mean?
Yeah, I mean, it's a second degree question. Still one.
There's a log n
Like
factor that might probably comes from the algorithm. I don't think it's from the analysis. And then so by using those propositions on the previous slide about stability of ERM, stability of regularized ERM, which of course is our subroutine here that we're relying on every iteration in line 4, and about how it generalizes well, and about how the noisy SGD with selective clipping approach to solving regularized ERM gives us an approximate risk minimizer. We combine those in the right way, along with some techniques from Feldman et al., and we're able to prove our main theorem, which is that upper bound, near optimal excess risk upper bound. Any questions?
There is a question. So if you basically what's going on, for instance, so you're with this successive localization, it's the same question as the one for Feldman and company, but just still nothing is strongly convex here, right? Okay, regularizer.
That's why we regularize.
Because you regularize, you can localize. That's why.
Exactly.
Okay, I understand.
Yeah.
But then in the end, it turns out that somehow magically you did not regularize. Like in the end, did you solve the regularized problem, or is it the non-regularized problem?
No, in the end, so yeah, in each
Result of this algorithm.
at the end of the day, we get a bound directly for the convex loss function. But of course, the analysis relies on like relating the solution to the regularized problem to the solution of the original problem. And that's basically, we do that through our novel
I
results of
understand that.
stability.
It's a trick that keeps reappearing and in many works. It's like people, yeah, I understand.
Yeah.
Every time you decrease lambda twice, so you get, or like increase lambda twice, you get a twice smaller radius. So you kind of always, one ball is kind of touches the other, and that the balls keep decreasing. And so
Exactly.
you're kind of where you were supposed to be.
Yeah, it's a really nice idea. The localization idea is not around, but yeah, we just are applying it, using it as part of our algorithm and analysis. So that was for convex. We also address strongly convex differential private stochastic optimization. In this case, if we assume strong convexity of the loss and all the other assumptions stay the same, bounded kth moment, then we can actually get better excess risk. So we're essentially getting the square of the convex rate. So instead of 1 over square root of n, now excess risk goes down like 1 over n. And 1 over n here, r squared over mu times 1 over n is the optimal non-private rate. So again, the second term here is the price of privacy. And it's exactly the square of the convex price of privacy. Again, this is optimal up to a logarithmic factor. And the proof here is very simple. Basically, once we close the convex case, strongly convex follows as an easy corollary. There's this folklore reduction of the convex case, which was presented, I believe, first in this paper by Hazan and Kale, 2014. And it essentially just involves running our optimal convex algorithm log n times and using strong convexity each time to shrink excess risk a little bit more. And so that's kind of a nice trick too. But
Attention with rk squared, r2k squared over rk squared, because now there's a z. Rk is growing. It's not a constant power k. It's d power, like r2k is d power k in the normal case. That means that, so it's kind of like square root of d that might be lost there in translation. Like if this were with supremum outside,
yeah,
then this would have been like reasonably a constant. It's kind of like moments of
I see what you're
one-dimensional Gauss.
yeah. So we do, again, that's a good point. And we do get upper bounds for that case with supremum and expectation switch, where r gets placed with this other parameter that's smaller. But in that case, we require sub-exponential distribution. So it's just an additional assumption gives us that no problem.
Okay.
So other results in our paper, we also proved tight lower bounds, which establish optimality. So the idea of lower bounds is we reduce stochastic optimization to mean estimation. And we reduce mean estimation to identity testing to choose identifying the right distribution and some packing. And then we use a differentially private strengthening of Fano's inequality to prove the lower bound on the misclassification error. We also give linear time algorithms for smooth losses, as I mentioned, which have improved excess risk versus prior works, and they're optimal at certain parameter regimes. For example, if the population loss is sufficiently smooth, then they're optimal. We also address the non-convex case under the PL assumption and give it near optimal algorithm in linear time. And this excess risk nearly matches a strongly convex rate, but it's achieved without assuming convexity. And the PL assumption is satisfied by some practical models such as wide neural networks, also convex models like linear regression and lasso satisfy the PL. And this is a linear time algorithm. So in summary, we talked about the differentially private stochastic optimization problem, which is a fundamental problem in private statistical machine learning. We talked about how most previous works on DPSO gave excess risk bounds that grow with the worst case Lipschitz parameter, and that this is not very practical. And so to address that shortcoming, we built on a line of work that considered the problem under the bounded kth moment assumption, as opposed to requiring uniform Lipschitz continuity of the loss. And we established the first asymptotically optimal excess risk bounds for convex and strongly convex loss functions. We described our algorithm, which involves main ideas of it are selective clipping, regularized ERM, and some new results about the stability and generalization of regularized ERM, and combining that with the iterative localization technique of Feldman et al. As I mentioned, in terms of the novelty of our proof, it's mainly these new results on stability and generalization, showing that you don't need smoothness, you don't need uniform Lipschitz continuity to get these guarantees. And then we also gave some linear time algorithms and a near optimal algorithm for non-convex loss. So a couple of open problems stemming from this work. One is the question of whether it's possible to achieve optimal excess risk in linear time. So our linear time algorithm is not optimal in every parameter regime, and our optimal algorithm is not linear time. So is it possible to get the best of both worlds? Not clear, but I suspect it probably is, but it would take a very new algorithm.
What is nonlinear time in the optimal algorithm?
So our algorithm, because you're right that we take each batch of samples disjointly and only use each sample once. But once we take a batch, we don't just do one gradient computation. We actually perform many steps in order to find the regularized ERM. So we minimize the empirical loss corresponding to this batch, which takes like
Oh, so you
potentially
need to
an
do very
iteration.
rough minimization to do something linear time.
Yeah.
Nice.
Yeah, so our algorithm runs in roughly like n squared steps. And then the other question is about non-convex beyond the PL condition, right? For finding stationary points, for example, that's a very wide open problem in private optimization is, you know, how small can we make the gradient norm, for example, for training deep models, deep neural networks. All right, thank you very much. And
Question.
Yeah.
Can you go back to the one of the last theorem? Yeah. So this one is optimal or non-optimal one?
it's optimal up to the lower bound basically looks exactly the same, except it doesn't have a logarithmic tilde on top of the O, and also instead of R sub 2K, it has RK.
Yeah. So this one is non-linear time.
This one's nonlinear time also.
Yeah, so I'm wondering, so when I look at this price of privacy, I'm thinking, I think this term can get really big, is it? If you require some level of privacy, say if you require your lambda, not lambda, delta and epsilon to be small.
Yeah.
I wonder if have you tried any simulation to see it, to get some like empirical value for excess risk, so you get some idea of how this costs you.
Yeah, so we didn't implement this algorithm because it's not very practical. This is the one where it's like the localization thing, to be honest, isn't the most practical. I think our linear time algorithms, we did run some experiments on, those are more practical. They're sort of more standard variations of noisy clipped SGD, like the first the sort of naive algorithm that theoretically isn't optimal, but actually works decently well in practice. So you're right that if D is very large, then the cost of privacy can be huge. And there's a big gap between the non-private SGD and these algorithms. But if it's like a problem that's not too hard, like logistic regression with a fairly, reasonably small data set, then the DP algorithms actually do like fairly well. Like, I don't know, like they can get like, you'd see like some results where they get like 80% accuracy on MNIST as opposed to like state-of-the-art private gets like, non-private gets like 95% or whatever.
Reminds me what D is, it's the dimension.
D is, yeah, the number of model parameters. So like if we're training a deep neural network, like one of these language models, for example, might have D in the billions, like ChatGPT or something.
So it's much harder for ChatGPT to achieve privacy.
Exactly. Yeah, at least, or maybe not harder to achieve privacy, but harder to achieve privacy and accuracy.
With accuracy.
Exactly. But yeah, in practice, we think of epsilon as being like a small constant, like epsilon equals 1 is a very strong privacy guarantee. That's fine. So you can almost ignore epsilon in this expression. And then the cost pretty much all comes from D if you also ignore this logarithmic factor.
Yeah, this is a little bit counterintuitive because when you have a very large model, it's very easy to get, like if you have just change one input, it's kind of easy to get lost in the those long process of the calculation. But
Yeah.
It's actually the other way around.
Yeah, I guess I think of it as like the deeper, the more complicated the model is, it's like sort of the more inclined the model is to memorize stuff. So in a sense, like preventing it from memorizing is going to take more work. It's going to have more of a cost in terms of accuracy. And there's more parameters to privatize along the way.
So at the very beginning, you change the Lipschitz condition to the case-bounded condition, right? So what do you lose?
What do we lose? Right. So if we assumed uniform Lipschitz continuity, then instead of R here, we'd have LF, and instead of this expression would just become a 2.
Right.
So as K goes to infinity, we get the Lipschitz result. But when K is finite, then this expression is going to be bigger than the expression if we replace this by a 2. Yeah.
If I consider the class of losses that are just like that, quadratic, with unknown, so basically if, but I don't know, let's say the covariance of X, so I can adjust, kind of normalize it, standardize it. Or in other words, if a priori bound I have on W is such that it's on double view. So if I standardize X, the bound will become an ellipse. So it's not a Euclidean kind of usual kind of ball constraint problem anymore. Then in this class, it seems that I'm doing mean estimation, not mean estimation, but linear. Like I'm doing private linear regression, right?
Okay.
With random design.
Yeah.
I know that even for private mean estimation, which is basically denoising, so this problem without the design.
Right.
Even this problem, like, I mean, now it's closed, but it's been like, it's not an easy one in the end. I mean, now people understand how to do
So
it.
private mean estimation is the same rate as this, by the way. So
Okay.
our lower bound is proved with a reduction to mean estimation.
No, but like in the end, there is also parameter, right?
I was talking about private mean estimation of distributions with bounded kth moment, like with L2 norm as there.
Right, but what is the moment then? Because I'm bothered by this supermoon side of the expectation. That's the problem. And this problem does not appear with mean estimation. It is related to randomness of the design.
I mean, so this is for.
This is mean estimation,
yeah.
yes.
And in this case, this is strongly convex, so our upper bound applies, and it turns out that this is the hardest, it's for the lower bound too. So the rate is exactly the same.
Okay. Like this thing does not have any strong convexity there, right? I mean, it has, but like parameter is one. It's not.
Oh,
it's
yeah,
itself.
rescale or
Design.
whatever.
This is a round function. That's its
Yeah.
application is identity, like scaled identity.
Right.
The problem with this one is that the Hessian is not
I
identity.
see. Yeah, this is interesting. I'll consider this. That could be interesting to pursue if to try to close the gap between the supreme and expert. Seeing what because yeah, maybe this is an example where the rates actually differ, right? For the classes, just all
I'm
convex
asking,
problems.
I'm asking because even for robust mean estimation, but without any privacy, but with random design,
Okay.
without making silly assumption that the design is isotropic, so its covariance is identity. So without assuming this, recently people maybe a year, 2 years ago started to really realize that it's just a silly assumption. And it's a non-trivial problem at all, like to do not mean estimation, but to do robust linear regression with design that is like you want a prediction bound that is like D over N without depending on the covariance, because it should be a fine invariant. It's a fine invariant problem, but at the same time, a covariance of the design is just something that you don't know. Like essentially in the end inside, you somehow need to estimate the covariance, like
Yeah, I'm not. Let's talk about it offline.
yeah, just like.
It's a good point. Okay. Any other questions? All right. Thank you.
I mean, I understand there is.
Yeah. Sure. Yeah. I'll see you. Might stop by sooner.
Basically,